Hey guys, Ms. Marusik here, and in this video we're going to talk about ionic bonding, a little bit of an introduction to some of the properties that we see with ionic compounds, as well as a little bit of an introduction to a concept called lattice energy that deals with the energy that ionic bonds would have. So to kind of start us off here, just some basic properties that might sound a little bit familiar from pre-P. Ionic bonds form with a substance with a low ionization energy, so something that's really easy to remove an electron off of, so something like a metal, will completely give its electrons to a substance with a high electronegativity, something with a really big pull to bring in those electrons, and as we know, that would be some sort of non-metal. Non-metals tend to have a much higher electronegativity. So what happens is the metal atom will lose that electron and become a cation. And when it undergoes that process of going from something being neutral to all of a sudden having a positive charge, we do call that process an oxidation, or we say that the atom has become oxidized to a cation. On the flip side, of course, the nonmetal, in pulling on those electrons, would gain the electrons to become an anion, to have a negative charge. And we would say that the process was a reduction, that the atom got reduced when it became that negative anion. So as far as kind of identifying what we typically see in an ionic compound, we typically see a metal with a nonmetal. I know most of us remember that from naming and formula writing. As a reminder, we can replace a metal with another polyatomic ion cation. So for example, like ammonium is our one that we are familiar with. And then our nonmetal could be replaced with an anion, such as a polyion that has a negative charge. So, carbonate or chlorate or phosphate or sulfate or nitrate or any of those, you could replace that nonmetal with that piece. So you could get different combinations here. Obviously, you could have a metal with a polyion. You could have ammonium with a nonmetal. You could have ammonium with a polyion. So we can get lots of different combos there. All right. Now, most of the time when we are trying to predict whether or not a substance is ionic or not, we will use this kind of basic format to figure out, is it ionic or covalent? That works 99.999% of the time. Every once in a while, though, we might be asked to double check whether or not a compound actually is ionic. And in order to be able to do that, we would need to look at electronegativity values. Now, as a reminder, electronegativity is that pull to bring in an electron. And so what has to happen is that one of our substances has to have a big enough pull on the other element's electrons in order to completely take it away from that other element. So most books would agree that in order for a compound to be considered ionic, we need to see a difference in electronegativity between our two ions of 1.7 or greater. So what that means is if I go look up the elements and their electronegativities and I calculate the mathematical difference between them, if that value is 1.7 or greater, then we would consider the one element to have a strong enough pull to completely remove the electrons off of the other one. This is kind of a general breakdown. We'll talk a little bit more about this next time of kind of the breakpoints that we typically see with compounds. Typically, if it's 1.7 or greater on the difference, we would consider it ionic. By the way, the biggest difference you could possibly have is 4, because fluorine with the highest electronegativity has a value of 4. So if you put it with a substance that has a value of 0, that would be our biggest difference there. If we fall between 0.3 and 1.7, we typically consider it polar covalent. What that means is one of the elements is pulling strong enough to kind of sort of claim it more than the other one, but it's not enough to totally remove that electron off of the other element. If the difference is less than 0.3, then we consider that they're essentially pulling about the same, and so therefore we have a non-polar covalent bond. Now, I'll be honest with you, this is kind of a spectrum that not everybody typically agrees on, so depending on the textbook you look at, this might be a hair different. I always give the examples of earthquakes. My sister lives in California, and to her, a 4.5 earthquake on the Richter scale is nothing. To me, a 4.5 earthquake is kind of a big deal, To her, to be a big deal, it's got to be over 5. So, it kind of just depends on your perspective of what you feel like is pulling more or less. So, all right. So now, when we have an ionic compound, the ions arrange themselves in alternating positive and negative crystal lattice in a pattern structure. And you can kind of see an example of that here. We see kind of a regular repeating pattern, and that's what we mean by lattice. Lattice is a regular repeating structure to it. This particular example says that this is a diagram of the crystal lattice of NaCl. How can you identify which ion is sodium and which ion is the chlorine? Well, we're going to kind of have to think a little bit here about radius-wise what difference we might see. So the first thing I'm going to do is actually go find sodium and chlorine on my periodic table. Okay, I see that sodium as an atom would have 3 occupied energy levels. However, when that sodium that has 3 occupied energy levels becomes sodium plus 1, it's going to lose that entire 3rd energy level. So now all of a sudden it's going to be down to only 2 occupied energy levels. Okay, on the flip side here, we have chlorine. Chlorine also has 3 occupied energy levels. And I'm going to abbreviate EL for energy levels here. So when it becomes chlorine -1, not only will it maintain those 3 energy levels, but if you remember a little bit from last unit, we said that once it gains that electron and we gain some additional repulsions, it actually even gets a little bit bigger. So it's even going to be a little bit bigger than your normal 3 occupied energy levels over here. So when I want to go and identify now which element is which in this structure, I'm going to say, well, if sodium bumped down to only 2 occupied energy levels, that means it should be a lot smaller than the chlorine with its 3 occupied energy levels. So I would guess that this smaller ion here must be the sodium, whereas our larger ion here must be the chlorine. Okay, so now let's talk about another way we can kind of illustrate ionic compounds besides just drawing a crystal lattice structure like that. We can also do it with kind of a Lewis dot structure action. So to kind of see this in action, they kind of gave us a start here of a little bit of information. They show us here that we have sodium plus chlorine yielding the sodium chloride, and what we're going to do is we're going to draw some dots around this. So thinking about sodium as an atom, sodium only has 1 valence electron, so I'm going to put that 1 valence electron around it. Chlorine, on the other hand, is in group 17, so it comes with 7 valence electrons. And if you remember, when we do this with atoms, it kind of looks something like so. We kind of, put 1 on each side before we double up, although here what happens is we get that 1 unpaired electron happening. So what happens is that sodium, and kind of willing to give away this electron, chlorine has a really big pull to take in that electron. Chlorine has the bigger electronegativity out of the 2 of these elements. So what will happen is that electron's going to sneak over here to chlorine. So as a result, what would happen is that sodium will have lost its valence electron around it. So we would end up showing no dots, insinuating then that the previous energy level would have been the filled one. I'm going to put brackets around it to show, though, that it's not normal sodium, and I'm going to give it a +1 charge. For chlorine, now all of a sudden, it's going to have 8 valence electrons around it. I'm going to, again, put brackets around it to show that it's an ion, that we did something a little extra to it. And, of course, when it gains that 1 electron, it takes on a -1 charge. And so we can see there a final Lewis dot structure for sodium chloride. Now, keep in mind, this is a big difference than what we saw with covalent Lewis dot structures, which we'll talk a little bit more about next class. Covalent Lewis dot structures are the ones where we show them sharing and we show it all bonded up with, like, lines, and we have to get everybody to 8 valence electrons. This is totally different. When we're doing ionics, we want to have those brackets with the charge, and we want to make sure that the charges are canceling each other out. We want to make sure that the cation is losing as many electrons as the anion is gaining. So to see that in action here, it wants us to, hey, draw a final Lewis dot structure for calcium bromide. Now you could do it almost the same exact way if you wanted to, but I'm going to be kind of sneaky about this. I'm going to do it a little bit kind of a shorthand way to get straight to here. So I'm going to think about calcium for a minute. I know that calcium is in group 2 on the periodic table. So normally it has 2 valence electrons to it. However, it's going to lose both those valence electrons because I know it's in group 2, and that usually does a +2 charge. So I'm going to come over here and I'm going to say, hey, I'm going to have the calcium. It's going to lose the 2 valence electrons that it has, so I'm going to draw no dots around it. And I'm going to come over here and put a +2 charge with it. Okay. On the flip side, bromine, just like chlorine, is in group 17. So normally it has 7 valence electrons. But we also know that if it's in group 17, it likes to make a -1 charge, which means it loves to pull in an electron. So when it does that, I would bump up from 7 valence electrons to 8. So when I draw that bromine in here, I'm going to draw all 8 valence electrons. I'm going to again draw brackets. And I'm going to draw a -1 charge. Now I have to be careful here. I see my charges aren't balanced. So just like what we did when we wrote formulas of compounds, I have to go and balance out these charges. I need to make sure that this calcium that's giving away 2 valence electrons, that there's enough bromines to take on those 2 electrons. Right now, this bromine is only taking on 1 of those. So what that means is I do need to draw an additional bromine. Proper notation is to put it over here on the other side. Proper notation is to alternate positives and negatives, if all possible. Sometimes it gets a little tricky, like, you know, if you have 3 of one ion and only 1 of another, that gets really tricky to alternate. So sometimes you have to put an ion above or below to make it work, okay? So don't panic. Do the best you can with alternating. But the big thing is that we want to draw 2 bromine ions versus the 1 calcium ion. That's kind of the main important thing there. All right, some other properties that we see with ionic compounds include that ionic compounds tend to have very high melting and boiling points. That has to do with the fact that they have very strong, what are called ion-ion forces present. And so you have to have a lot of heat, a lot of energy in order to break those forces that are present. When we are melting ionics, we're actually breaking the bond and not just IMFs. We're going to talk a lot more about that next unit. As a reminder, they will not conduct electricity as a solid, but they will if it's a liquid, if I melted the ionic, or if I dissolved it into a solution. That is because in order to conduct electricity, we have to not only have charged particles, which we have because we have ions, but those charged particles have to have the ability to move. And as a solid, those charged particles cannot move positions. They are often, but not always, soluble in polar solvents like water. For example, we know that table salt does dissolve in water, but there's some ionics that don't dissolve in water. That comes from solubility rules. However, an ionic will never be soluble in a non-polar solvent. So like, for example, if you put table salt into oil, that will not dissolve. Might be suspended in there, but it won't have officially dissolved. Also, ionic compounds tend to be brittle, which means they are not malleable or ductile. If I kind of break them, they'll just crumble into pieces versus being all bendy and flexible. They can also often be cleaved. Now let me kind of talk about the cleaving here for just a second. You can kind of see some pictures down here at the bottom. First off, here is where they are kind of hitting into this ionic structure. And what happens is because the like charges repel, when I kind of hit into it and I shift that structure, that lattice structure, what happens is that the positives and the negatives end up repelling each other and end up cracking in very specific patterns. So what happens is that we see breaking along planes. So like, for example, this is NaCl that has been broken. You can see another picture here where they're breaking it, and you can see it breaks off into really flat planes, even though I'm not like sanding it or doing anything special to get that appearance to it. By the way, depending on what the lattice structure looks like, these planes might either be flat like this, or they might be at angles to one another. So here we see kind of 90-degree bends, but on other structures that might be more like 45 degrees or 30 degrees. It just depends on what the lattice structure, what this pattern looked like originally for that substance. All right, let's go ahead and take a moment and flip the page, and we're going to talk about lattice energy. All right. Okay, so a little bit about lattice energy here. First off, I want to talk first about the enthalpy changes that we see when an ionic compound is forming. Because it's not just as simple as I put these 2 ions together and bam, I get my compound, okay? It says here, hey, as a reminder from last unit, the process of ionization, losing electron from a gas to form an ion, requires an input of energy. So that is an endothermic process. So in the process of trying to form, say, sodium chloride, one of the first things that has to happen is that we have to take sodium and change it into sodium +1 with an electron. We have to undergo that ionization process, and that process is endothermic. However, we also have to take our chlorine and we have to make it negative. So here I actually need to make it gain an electron. When chlorine gains an electron, because it really likes to be able to do that and pull that in, it actually is an exothermic process. And actually it undergoes a process called electron affinity where we're pulling in that electron here. Now, this is not the only two processes that have to occur in order to form sodium chloride, which is kind of crazy to think about. So I actually want to talk about this lovely table down here for just a minute. This kind of, I don't know, chart, if you will, with all these values on it. This is what is called the Born-Haber cycle for sodium chloride. Now, I have really good news for us. You do not need to memorize this cycle at all. Like, don't even stress about it. However, what we want to be able to do is kind of understand that there's a lot of energy changes that go into forming sodium chloride, into forming table salt. First, you would have to start off with solid sodium and convert it to a gas. That takes an input of energy. Then you would have to take your chlorine gas that's diatomic and break it up into a single chlorine atom. That also takes an input of energy. Then I have to ionize, as we talked about a minute ago, that sodium and get it to change over into sodium positive 1. So there's that process of ionization that we mentioned just a minute ago. Then you have to also take the chlorine that was a gas and convert it into chlorine negative 1, and that actually releases energy. Last but not least, we would come down here to join up the sodium ion and the chlorine ion to end up forming NaCl. Now, we're going to talk about something a lot when we get to thermochemistry, and that idea is that it takes to break, freeze to form. When these form a bond between them, that actually releases energy. So you notice that that process is negative. It's exothermic, okay, which is why this arrow goes down. However, if I was trying to, say, break this bond back up, if I was trying to take NaCl and split it back apart, takes to break says that it takes energy in order to break a bond. So if I was to do the opposite of this process, this negative 787 kilojoules per mole would end up becoming positive 787 kilojoules per mole. So with that said, we have all these processes that had to occur in order to form sodium chloride from neutral sodium and neutral chlorine. And long story short of it, we end up here with a net overall process here. Here's our sodium, our chlorine coming together to form NaCl. Not the ions, but the original atoms that we had. By the way, this equation right here relates to what is called the heat of formation. And we're going to talk a lot about heat of formation when we get to thermochemistry. But the heat of formation is basically forming 1 mole of some sort of compound from its individual elements in their standard state. However, I'll be honest with you. We don't really care about that part for right now. You're like, oh, great. Thanks, Marisa, for talking about all of that stuff. The part that we care about right now is what's happening right here. This process right here, there's that energy that we talked about, the negative 787 kilojoules per mole. That energy for sodium chloride is called the lattice energy. And that's what we're going to spend not only the rest of this video talking about, but also the next video after this one. Lattice energy is defined down here. Okay, it says that lattice energy is the energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. So not into the neutral elements like we see with heat of formation, but rather just into the ions. Okay, now you notice here it mentioned that we are separating, okay, whereas up here we actually put these things together. So if we were to flip that equation around where we take the NaCl as a solid and break it back up into sodium positive 1 as a gas and the chlorine negative 1 as a gas, the energy associated with that, the change in heat, instead of having a negative 787, would have a positive 787 kilojoules per mole for its lattice energy. So again, this value right here, that is our lattice energy for that particular compound. Now, here's the deal. Every ionic compound has a lattice energy associated with it. How much energy would it take to break apart that bond into its ions. Okay. Now, we talked a lot about attractive forces last unit. Well, let's think about this for a minute. The stronger this bond is held together, the more attractive forces you have. Do you think it would take more or less energy to break it up into its ions? Well, let's be real here. If things are held together more tightly, I'm going to need a lot more energy to undo them. So what that means down here is that if lattice energy is high, that means it took a lot of energy to break the ionic bond, meaning that the attractive forces were stronger. And we would say that the bond itself was strong. So what we're going to do in the next video here in just a minute is that we're going to look at what could potentially make this amount of energy higher or lower for an ionic compound. What gives some compounds a higher lattice energy value than others? Now, one last thing I do want to mention, because obviously lattice energy should have a positive value with it. However, I will warn you that because technically back here in the Born-Haber cycle, this process did have a negative value with it. Some books still report lattice energy with a negative value. Here's what I'm going to tell you. Don't panic about the positive or negative, okay? It mentions down here that we are not going to stress about the positive or negative on it. What we care about is the magnitude, the size of that number, okay? So, with that said, hopefully this kind of refreshed your memory on a few things having to do with ionic properties. We are going to talk more about the idea of lattice energy in the next video. If you have any questions or need any help, please feel free to email me. Bye, guys.